Okay, next section, 10.7, vector functions, which you saw in AP Calc VC. You had the vector valued functions. So the derivatives and integrals of vector valued functions you have seen before. Graphing of them you've seen before. The difference here is that we will do them in 3D, which can get a little bit hard to graph, but basically the same idea. There'll be a couple tricky problems that we go over here. But just remember here, when you have a vector valued function, your domain would be real numbers for us. And it's kind of like your parameter. We usually talk about your input as being t, okay? And then your range or your output is vectors, okay? Or your r of t, okay? Your r of t is actually a vector that is a function of t for the x component, a different function of t for the y component, and a different, or the same, I guess it could be, but that'd be like a coincidence, function of t for the y component. Or we can write that in linear combination form. Okay, your input is t and your output is a vector. And remember that vector goes from the origin to a point on the curve. Okay, so the vector with an initial point 0, 0, 0 and a terminal point, f of t, g of t, h of t. So the vector connecting those 2 points. Okay, so let me just do one more little drawing here. 3D it. So, you might have a vector valued function that in space looks like that. And maybe you've got, let's see, maybe like right here is r of 1. And then maybe another one here. Like maybe this is r of 2. Okay, so by finding all those different vectors that are pointing to line or points on the curve, you get your entire curve. Okay, so let's just kind of take a look at an example of one. Let's say that we have the vector function r of t equals square root of t minus 8 log base 2 of t plus 8 sine t pi. Okay, so we can do things like r of 24, which I'll give you a second to think or pause. Just plug 24 in for t. So we'd have the square root of 16, which would be 4. We'd have log base 2 of 32. 2 to what power is 32? That's 5. And then we would have the sine of 24 pi, which would be 0. Okay, so we could evaluate a vector function. We can get the domain of a vector function. In this case, you got to think about each function separately. So for the square root of t minus 8, we would have to have 8 or greater for t. For your log base 2 of t plus 8, we would actually have to have t plus 8 would have to be greater than 0. So t would have to be greater than negative 8. Okay, and then your sine of t pi, we could have all real numbers there. Okay, so where is the overlap or the intersection of all that? Well, that would be t greater than or equal to 8. So your domain would be from 8 to infinity. Okay, your range here too. Actually, I'm not going to do range because you'd have it could be numerous vectors. I was trying to give the fact that your x component would never be negative. But we'll do something different for that. Let's do your limit as t approaches 8 of r of t. So again, with this one, you think about what vector is our limit here. So as t approaches 8, we're going to 0. As t approaches 8, we're going to log base 2 of 16, which is 4. And as t approaches 8, we're going to the sine of 8 pi, which is 0. We could do your limit as t approaches infinity of r of t. What we would get here is the x component goes to infinity, the y component goes to infinity, the z component oscillates, so it does not exist. So we would say that limit does not exist because of the z component. Okay, it's not approaching any value. And any rules of continuity would apply to r of t is continuous at t equals a if the limit is t approaches a of r of t equals r of a. That's your same definition of continuity applies. Okay. Take a look at another example here. We have an example. If we have r of t equals 3 minus t, 3t plus 5, 2t minus 1, and we're asked to describe that, which is pretty common. For this one, you need to recognize that this is linear. This is your segment, okay? Actually, line. It's not a segment because we haven't limited the domain of t. But you should recognize this from section 10.5, that this is the equation of a line in 3D, okay? Not only that, but each piece of it, the x component, the y component, and the z component, those are all lines as well, okay? So this is a line. And using what we learned in 10.5, don't forget, I'll even write it over here. In 10.5, we learned r equals r naught plus tv. That's your equation for a line. Okay, so this would be a line that goes through 3, 5, negative 1. Okay, and again, that's from the non-t parts, okay, which would be from that piece. And parallel to, and that would be vector negative 1, 3, 2. Okay, and that again comes from the t pieces there, which would be this part. Okay. Another example where you're asked to describe, let's see, if we had t squared t2. Okay, this one is not as straightforward, but we can do something similar to what we did with the quadric surfaces, is you kind of think about what's going on in each plane. So think about like x equals t squared, y equals t, and z equals 2. So in your xy plane, x equals y squared, right? If x is t squared and y is t, in our xy plane, we have x equals y squared. So we have a parabola. Okay, so if you were just looking in the xy plane, your projection of this curve into your xy plane is your sleeping parabola, right? Your guy that looks like, oops, this. Okay. In your yz plane, we would have y equals t and z equals 2. That's just going to be a line. So it doesn't matter what, z is just always 2. So you're just going to have that y equals whatever, it's linear, okay? So in your yz plane, let's see, I'm going to do a different color here actually. just going to look like, I don't know what I did. I guess because it's the negatives. It's just going to be z is always 2 and y is whatever t is. Okay, and then you're going to get in your xz plane. You're going to have x is t squared and z is 2. That's also just going to be linear. Don't let the t squared fool you. You're going to have x, y, z. Z is always going to be 2, and x is going to be whatever t is squared. Okay, and then that's the projection. Okay, so again, if you're thinking about like shining a flashlight or whatever, just ignoring the other dimension. Okay, so if you kind of put this all together, and I don't want to scroll down too much, what you're going to get here is that this graph is a parabola that goes through the point 0, 0, 2 and is basically kind of floating above your xy. I don't know if that's a good drawing. It's this parabola here that would be flat in the xy plane shifted up 2 units. Okay, so think about your parabola again that's just flat and that xy plane was equal to 0. We're going to shift it up 2 units. So then you can think about, like, if you look down on it in the xy plane, you see a parabola. If you look to the side of it and just look at the yz plane, it would look like a line, right? Think about looking at that thing straight on, like you are standing here. You're a little stick guy. Actually, I'm going to use the one where, think of this as being shifted up 2 units. Okay. So like if you're standing down here, looking down the x-axis at it, you don't see the curvature to it. You just see the flat line. Okay. If you're up here in the z direction, looking down on it, like the laser beam eyes here, you see the parabola, and you don't see that it's up or down. You just see the parabola. Okay. You don't know that it's 2 units up because you're way at the top. If you look over here, okay, again, you're looking straight at it. You only see the line. You don't even see the 2 branches of the parabola. We can also get to the fact here. What this is showing you is that x is always positive, right? We drew this purple guy here, but really this part doesn't even exist because if x is t squared, x isn't ever going to be negative. Okay, so you got to kind of think about all your 3 different viewpoints of this. If you're standing down z-axis and looking into it just in the xy plane, if you're standing down the x-axis and looking at it just in the yz plane, if you're standing down the y-axis and only looking in the xz plane. Okay, we'll do another one here. It's a little bit trickier, and I think since this video is getting long, I'm going to split it into 2. But we'll do a couple more examples here. This one's a little bit different. We have r of t equals 2 cosine t I plus sine t j plus tk. And again, x is 2 cosine t, y is sine t, and z is t. Okay, so you can think about this one in your 3 different viewpoints here. And this one gets a little tricky. Let's see. In your xy plane, you guys know from calculus that you relate cosine and sine using the fact that sine squared plus cosine squared equals 1, right? So we don't quite have it here. It's not quite x squared plus y squared equals 1. It's 1/4 x squared plus y squared equals 1, which is an ellipse, right? It goes down 2, back 2, and then 1 and 1. Okay, so looking down from standing at the top of that Z pole, think about it like that Z axis, like a flagpole. You're up there looking down, you see an ellipse. Okay, so whatever the curve is doing, it's following that shape of the ellipse as it goes higher or lower. Okay, let's take a look here. If we look at the YZ plane, we would have Z equals sine Y. So in the YZ plane, and this is weird, you have a, let me make sure I get this right. You have a sine curve. And it goes like, let's see. I'm going to get it right. Oh, let me think here for a second. Let's see. So I'm trying to, because I'm thinking of the graph of y equals sine x, which looks like this. Okay, so I want z. This would be z and y would look like this. So I'm thinking about my positive z and my positive y. For some reason, my brain is not functioning. That doesn't make any sense. I'm going to come back to that one. You know what? Here, I want you guys to do what I would do to get this right in my brain. I'm going to apologize. That's a terrible. I should have thought about that a little more. You know what I was thinking is that it goes up and down. And I'm sure I'm going to, it's going to come in my brain here in a second. But anyways, you can think about some points too. So if you can't quite wrap your brain around that, and I know what I'm doing here. It's not translating to the video. This is embarrassing. Okay, anyways, you guys don't say anything. If t is 0, think about what point you're going to have. Okay, so if t is 0, we have the point 2, 0, 0, right? And pick good values of t. Like you're not going to plug in 1, right? You're going to plug in like pi. You're going to have negative 2, 0, pi. If t is, maybe we want to do pi over 2 instead. You're going to have the point 0, 1, pi over 2. You can think about t being 3 pi over 2. You're going to have 0, negative 1, 3 pi over 2. I don't know why my brain isn't wrapping around the 2D part, or the 3D part of this. 2, 0, 2 pi. Like that. Okay, so you can kind of get some points on it. See, and now it came to me. And because I kept thinking about it. In your YZ, you're going to have y equals the sine of z. So it's going to be a sine curve that's more like this. Okay. Yeah, I couldn't figure out why. I think I had when I was trying to visualize it, I think I was mixing up x, y, and z. And then in your xz, you're going to have x equals 2 cosine z. So that is going to be, basically, it's going to be a cosine curve, right? Okay. Not the best drawings, but what I'm trying to get at here, and what I'll illustrate too with those points, is that you kind of have like a weird spiral going on, and it's always kind of following the track of this ellipse, but it's like spiraling up and down. Where if I flatten it and kind of look it to the side, I would see a sine or a cosine curve. Okay, so let's put it all together. Okay, some points that we know that are on it. So we've got the 2, 0, 0. Again, you can scroll up if you want to see those again. But the 2, 0, 0, the negative 2, negative 2, 0 pi. Okay, so think negative 2 in this direction. 0, but then you're up vertically a distance of pi. Okay, you've got the 2, I think I have mine a little bit out of order, 2, 0, 2 pi, and you're back over here. I think I made that a little bit too high. Okay, but you're back out 2, 0, and then up to 2 pi. Okay, so you can kind of you're getting that zigzag back and forth that you would see in the XZ plane. You can kind of see that, making a cosine curve there in your XZ plane with a amplitude of 2. Okay, we can get those in-between points also to get us a better graph here. When t was pi over 2, we were at 0, 1 pi over 2. Okay, and then at 3 pi over 2, we were at 0, negative 1, 3 pi over 2. Okay, so this was r of 0. Then here would be r of pi over 2, which again was at 0, 1 pi over 2. This one was at 2, 0, 0. And then, so we're kind of, I'm going to choose a different color here. Okay, we're kind of curving around to that guy. All right, and then we had r of pi, which was at negative 2, 0 pi was the terminal point there. Okay, so now we've curved back in onto the x-axis again. Okay, and then we've got over here r of 3 pi over 2, which had a terminal point of 0, negative 1, 3 pi over 2. Okay, and I think my scale's probably a little bit off here because it should be a smooth, here. Here's what I'm going to do. Put this one up a little bit more. It should be above. Okay, and then this last one, r at 2 pi, which had a terminal point of 2, 0, 2 pi. Okay, and so you get this curving back around. Okay, so we get this little kind of curve. This point is directly above this point. Okay, and it's kind of done this curve out and then back around. And so it would eventually look like this spiral here if we kept going. Okay. Let's see, I'm going to do one more, and then I'll stop and change it to a second video here. The last one is, sometimes you have to come up with the vector function, not often, and not for anything that's too difficult, and this is just from 10.5 again. You segment from 3, negative 5, 2 to negative 1, 8, 9. Okay, so we know when we do a segment, it's 1 minus t. This is from 10.5 again. Okay, for 0 less than or equal to t less than or equal to 1. Okay, so we would have 1 minus t times 3, negative 5, 2 plus t times negative 1, 8, 9. And we can expand that out, and we would have 3, negative 5, 2 minus 3, minus 3t plus 5t. Oh, I got too many negatives. I'm going to change that to plus. A negative 3t plus 5t minus 2t. Oops. and then plus negative t plus 8t. I keep putting pluses there. And then 9t. And then what I can do is group them. So we would have, let's see, 3 minus 4t, negative 5 plus 13t, and then 2 plus 7t. And that's for, again, t between 1 and 0. Okay, and that would get you your segment. And that's just from 10.5 again. Okay, I'm going to stop there and I'll make a second video for the remaining part.